All right. So we're starting with, well, welcome everybody. We're going to start with proposition 23 today. Are you taking that one or am I taking it, Kenneth?
I think you're doing it. I'm doing 24. I haven't read
Yeah.
23.
Yeah,
I,
right.
I only ever read the even number ones and I let you
Okay.
present the odd ones.
That's good because then I can complain about the gap in the proof of your one rather than deal with it myself. So I'll save that up for you. You can wait in terror while I do my tiny easy proposition. Okay, proposition 23. Says to construct a rectilinear angle equal to a given rectilinear angle at a given point on a given says straight line in my book, but on a given line. I mean, the meaning of this is not just to construct it on a given point, but to construct an angle, one of whose sort of bounding sides is also a given line. So here's the diagram. Well, I'll start with introducing letters. So let AB be a line.
Have you said what rectilinear means in the previous lecture?
No, yeah, it doesn't really say either. I think it's content free. It just means angle. So I should have skipped it. I don't know if you have a different opinion, Kenneth. I don't think it means anything.
I don't think it means anything either, but it seems like this terminology just appeared recently, even though we've been talking about angles the entire time.
Yeah, right. Yeah, it irritates me, so I'm gonna.
Yeah, I agree with you though. It
Kill
doesn't
it.
seem like it adds much. I'm okay leaving it there too, but writing takes time.
Right. Okay, so AB is the line, and we're going to let AB be the given point, and let DCE be a given angle. I think it's possible that it might have the content of something like an angle that is given together with two lines that meet it, like something like that. I have a sort of vague feeling that you could point to angles in figures that aren't actually bounded by lines whose vertices have been named or something, so maybe it has some content, but I think it doesn't matter. Let DCE be a given angle. Yeah. Okay, so here's the given angle. DCE. Yeah. Well, okay. So, really what we're given is this thing, right? We're given this angle where these two lines meet at C. And so it says, introduce points D and E on those lines. We might as well assume that there was two line segments, DC and EC, because we don't need any other part of those lines. And that's the angle which we're required to construct down here. Right? So that's what we're going to do. Okay, so join DE. Construct a triangle AFG from three straight lines. This was the proposition we did last time. Given three straight lines which satisfy certain inequalities, we can construct a triangle with those as the sides. And the lines we're going to choose are CD, DE, and CE. Now, they of course satisfy the constraints because they're already in a triangle, but the whole point is that actually we're using a little bit more than what proposition 22 gave us. or at least the statement of proposition 22. The statement of proposition 22 simply says we can construct a triangle with given sides, but really the proof shows that you can construct it on any line you choose, right? Because that's how you cut out the first side. So the proof shows that in fact we can construct on the line AB a triangle that looks like the following. There's actually a fair bit of that in Euclid where you use the proofs rather than the propositions. Okay, so that's the triangle we've constructed with straight line CD, DE, CE. So to be precise, CD is equal to AF, CE is equal to AG, and DE is equal to FG. That should line up with the picture above, I hope. CE, AG, DE, FG, yes. Now, since DC, CE are equal to FA, AG, respectively, and the base DE is equal to FG, the angle DCE is equal to FAG. Right, I mean they're the same triangle. This, technically speaking, is invoking proposition 8. So that's it. Right? We've constructed at A, on the line AB, the angle FAG, which is equal to the angle DC. Any questions? Yeah, maybe I'll express my concern about the proof you're about to do, Kenneth, and let's see, what's the time? I mean, there's a lemma I think fixes the gap, but I don't know if it's actually a gap or not. So
we've got time.
Yeah,
We can talk about it.
Yeah, okay. If you look, maybe I'll just sketch the figure over here, and then you can tell me if you're concerned about this issue or not before we get into it. So here's my concern. So I'll just draw the diagram. The audience won't know what's going on, but that's okay. So this is a diagram we're going to draw. I feel like, how do I know this is out here and not inside?
Oh yeah, that's right. When I was looking through this proof, I kind of figured that even if it was inside of the oh, okay, well, it can't be inside, I guess, because we have to show that it's not inside.
Yeah, that's right. So there's a lemma. I figured out a proof. So if you agree this is a potential issue, I'll just give the proof quickly. Does that sound all right?
Sounds good. Yeah, you gotta show that it's outside, otherwise the diagram is all.
yeah. The diagram's doing a lot of work here somehow. Okay. Yeah. So I'm going to call this a lemma because Euclid calls all his things propositions, and I'm going to insert this lemma here. Hopefully you think it's a reasonable statement. Anyway, I'm going to attempt to give the English version, which it's going to be a bit awkward. Actually, Euclid's somehow very good at this. It's actually harder than it seems. In any triangle, if one side is greater than another, so I've just named two sides and an inequality between them. Those two sides meet at a point. And if I draw a line from that meeting point to the opposite side, which is what Euclid calls the base, right? The base is always the side that's not the two you've already talked about. From the common point to the base. That line is less than the greater side. So here's the diagram. So if I take a triangle, let me call this A, B, C. So suppose AB is greater than AC. And then draw a line from A to any point over here. Call it D. Let D be on BC equal to neither. Actually, one has to be careful about these degenerate cases in Euclid, which are often like the statement is no longer true. Join AD. The claim is that AB is greater than AD. So of course the length of AB as I drag this point along, it interpolates between AB and AC, and AB is greater than AC, so AD should be in between the two. Okay, so here's the proof. Well, so the angle ACB is greater than ABC. So it's been a while, but we spent quite a lot of time talking about angles. Greater angles subtend greater sides and so on. Right? And so this is what I'm using here. Because AB is greater than AC, that angle ACB has to be greater than the angle ABC. All right. Now, ADB is greater than ACB. That's by proposition 16.
That's the external angle business, right?
That's right, exactly. So the external angle on a triangle is greater, so that's ADB. This angle here is greater than both of these two. Right? In particular, it's greater than this one, but I just showed that one is greater than that one. So that means that is greater than that. Hence, ADB is much greater than ABC. But now I turn the argument around with the greater angle, the side subtended by the greater angle is greater than the other one. So
Nice.
AB is greater than AD. That's proposition 19. So I think that fixes the problem, but I'll hand over to you now, Ken.
Cool, thanks. I think that does fix the problem. I think, Dan, you're much more cognizant of these gaps than I am. I kind of just maybe trust the diagram a little bit too.
Well, it's inviting you to do that.
I did think about it, but then I thought, surely it's got to be on the outside. But I didn't figure out a Euclid style proof as you did, which is pretty cool. Okay, so proposition 24 is so now we'll see why we have that diagram that Dan drew. So I'm actually very bad with trying to replicate Euclid's kind of statement. I think I actually think it's somewhat harder to pass, but he does do this in a way that makes sense if you read the description a few more times. So I will write this down from Euclid, and then I'll give you guys the labeled version. So if two triangles, right? So if two triangles have two sides equal to two sides, respectively, to two sides, respectively, right? But one has the angle encompassed by the equal straight lines greater than the corresponding angle in the other. So, okay, I'm going to write this down. This makes absolutely no sense to me. Maybe it makes more sense to Dan. But One.
Your internal Euclid is not strong enough.
Nope. No. Has the angle encompassed by the equal straight lines greater than the corresponding angle in the other, then the former triangle will also have base greater than the base of the latter. Have a base greater than the base of the latter. So I guess you're kind of forced to do this if you don't label stuff, right? But the diagram is like this. So it's essentially the same diagram that Dan had earlier. We're going to draw a triangle. I'm going to label it ABC as usual. And I've done that thing again where I've tried to draw A, B, and C with straight lines. Okay, so we're going to have A, B, C, and then D, E, F, two triangles. I'm going to kind of draw them, leave me some room here to, okay. So I may have to hop over the other board to finish it off, but so we're going to let A, B, C, and D, F be triangles such that AC is equal to DF. So I'm just going to say A, B, C, and D, E, F triangles. I guess I'll put the proof on the other side and I'll finish the construction here with AC equals to DF. So I'll mark this on the diagram here. So AC and DF are the same. And of course, the other two pair, AB and DE are the same. AB and DE are the same. And AB is equal to DE, right? And so if the angle BAC, right, which is this one here, right, if angle BAC is greater than angle DEF, sorry, EDF, we want that top angle there, EDF, right, then the base BC is greater than FE. So I have to apologize to Dan for using symbols here, otherwise it wasn't going to fit on the page.
It's okay.
Okay, so yeah, so basically this is maybe the converse of, what was it, the greater angle spanning greater sides, or is this what this is saying?
It's a bit different
right,
because
so
the
this is
sides are equal.
Oh yeah, the side is slightly different actually. Okay, so the sides are equal. Okay, so the proof, let's walk over the other board. So Dan, are you still attached? I guess
Yeah.
you're attached, right?
Yeah.
I'm not. Maybe I should be. I don't know. I'm
Yeah,
close enough.
yeah, it's a bit tricky. If you're not attached, then you should try and stand a bit close to me because the audio is pointing at me.
Fair enough. All right. So as long as you could have heard me, it's probably fine, right?
Yep.
Okay. So the proof. I've got a whole board to do this, so this should be fine. But unfortunately, I'm gonna have to maybe go back to the other board to finish up.
That's fine.
Or
Just
maybe
tell me
that's
when.
also good because the recording's pointed at this page, right? So maybe what I'll do is I'll draw a small version of this. Hopefully, I'm not wasting too much time here trying to finish this. So I'm gonna draw a small version of this, and so we're not completely in the dark about what points and lines I'm talking about. But I have to do this to scale too, right? Like. Right, so we have to kind of do it like this. Okay. So, right. So these are the triangles we had earlier, A, B, C, and D, E, F. And we said that these sides were equal and these sides were equal. Maybe I'll just do it like this. And those angles there, one is greater than the other at the top. Okay, so here we go. So since, wrong color, so since angle BAC, that's that first angle here, is greater than angle EDF, right? That's this angle here. We can use the previous proposition to construct an angle with side ED, which is the same magnitude or the same size as the red angle BAC on top of it, right? And then draw the triangle and construct the triangle on top, right? We can construct, so by the previous proposition, which is 23.
Sorry to
Right.
interrupt you, but in order to invoke the lemma I proved, you have to say like AC is greater than BA or something like that. You have to pick.
Oh, yeah, you're right, yes.
And without loss of generality, you can do that. But
Yeah. Let me, yes, we needed that before I did this construction.
I think it's probably better if you just give the proof and just say that by lemma 1 it is on the outside or something. It's maybe not worth getting into the details.
Sounds good. Okay, so by 2.3 we can construct EDG, angle EDG, such that angle EDG is equal to angle, the red one, BAC. So I'll do the construction over here. So basically we're sticking a line here, which now I wanted to make it like this. So we're going to construct a line here and then join these up. Maybe we need to join these up too. I don't quite remember, but might as well join them up. So there's a G here, such that now this angle is the same as the other angle. Okay, and so I guess by, let's say by lemma, I guess F and D are on different sides of GE, right? So if we assume, was it AC is greater than AB? I guess it's got to be, right? AB.
Yeah.
F and D are on different sides. F, D.
Yeah. Actually, I'm sorry I interjected with that, because then people will wonder, well, what if AC is equal to AB, which they very may well be. It's still true that F is on the outside.
Yeah. Well, as you said, with these degenerate cases, right? You have to be careful about. But I guess for the most part we're good. Okay. So by we're up to, so by 1.3 or proposition 3, we can make DG equal to AC equal to DF. Yes. So basically, I've kind of jumped the gun here. We're also, by kind of drew the diagram without saying where this point G actually is. I guess we're doing this construction all at the same time. So by proposition 3, we can make this is certainly not Euclid's words. DG equals to AC equals to DF, right? So then I'll put a little line here. These are all the same, right? Okay, so halfway there. Now, since DE is equal to AB, so I'm going to switch over and write symbols now because we're almost out of time. DG is equal to AC, angle BAC is equal to angle EDG. So while we're saying all this, we're trying to make two triangles congruent, right, whenever we list these things. So all these by construction, we've kind of made them equal by the way we constructed all of the things that we did before. So by proposition 1.4, or proposition 4, I keep saying 1.4. I guess we're always on book 1. Triangle ABC is equal to triangle DEG. Okay, so we've got, ABC is the one on the left, that's all good. DEG is kind of the one with the 2 red sides, right? DEG is, they're the same. So, therefore, BC is equal to GE. BC is equal to GE. So BC is the base, GE is the base, so the conclusion is that these 2 lines are the same. And so finally, we have some bunch of inequalities, which will finish off the proof. So I'll just very quickly go there. So since DF is equal to DG by proposition 5, we have the angles DGF is equal to angle DFG. So DF is equal to DG, right? These are just because isosceles triangle. That's what proposition 5 says. If you've got 2 right, DF, DG are the 2 sides of an isosceles triangle. DGF and DFG are the 2 base angles, so they have to be the same. And so now comes the final inequality. So now inequality GFE, right, is greater than angle DFG. That's equal to angle DGF from what we've just shown. That's greater than angle FGE. In retrospect, I should have just left out all those angles because they're kind of in the way of all these inequalities. So for once, I'm going to just drop it because it looks ridiculous. So just these are angles. Just remember that the inequality signs are what they are. And so this tells us that by proposition 23, again, 23, BC is greater than FE, right? I think because, right, the angles GFE is greater than FGE. Yeah. So, yeah, so GFE is, maybe I'll just mark them, GFE is this one, right? And FGE is this one, right? And so, did I do this right?
Yeah, that's right.
Yeah. Okay. Sounds good. So that's the end of the proof. Sorry, it took a little bit longer than I thought.
No, that's great. Thanks, Ken.
Yeah.
Any questions?
Cool. But thanks, Dan, for patching the proof.
Yeah, I was a bit stressed about that this morning. Any questions? All right. I guess we'll end the Euclid session there. I'll take a moment to stop and start recordings. People can feel free to ask questions of Ken or start chatting about the next session. I'll be back in a moment.
Do we
Yep.
keep these suits to the and then we're staying here, so it's okay, right? We're not.
Yeah, the suits will.
But do we keep these suits in another one of your, like in deprecation, for instance? Do we still have them, or just in here?
There's another thing you can use to put on your suit again there, but at the moment they don't persist between parts of MetaUni. We'll do that at some point.
Cool, but this is super cool. I love this.
Yeah, just